to say what an enormous pleasure it is for me to be appearing here at your permanent seminar. It's a great pleasure, of course, to spend these 2 academic semesters as a visitor in Lisbon. And I want to thank everyone for taking the time out from your extremely busy schedules, as I know them to be, to take part in this session this afternoon. And a special welcome to those of you joining from other locations at home or elsewhere. And thank you, of course, to the 2 scholars and the 2 colleagues who very kindly introduced me for their extremely kind words. So this is a talk in philosophy of science. Most of my work is in philosophy of science is informed by history of science, as I like to think of it. But this is going to be mainly a philosophy of science talk. And it's on what I think is an important subject for any methodology of science, and that's the link between empirical evidence, the sort of evidence that we gain in observations and measurements on the one hand, and the structures that scientists posit in the universe, in the world, on the other hand. That link is, of course, extremely important. We receive data in some form from nature, from the outside world, but we want to do something with those data. We want to posit structures, as I'm going to be calling them, or phenomena, as you might also call them, in the world, on the other hand. And so I'm going to be talking about that link between empirical data and the posits that we make in the world. Let me give you an idea to begin with about the aims of my talk. Let me see, this might work. Does not work.
Try again. No. Try again.
Ah, there we go. Yeah, sorry, I am able to make progress. So the aims of my talk are the following. I'm going to start out from what I take it will be a fairly intuitive premise, a premise that I don't expect will be rejected by many people in the room. And the intuitive premise is that evidence of structures in the world come in the form of patterns in empirical data. That's something that many writers in philosophy of science at the moment endorse. But from that intuitive premise, which I think most people would find acceptable, I'm going to do my best to lead you in about 40 minutes now to a conclusion that many of you are going to find repulsive. You're going to find this conclusion not attractive, not acceptable. And that's the conclusion that empirical evidence, the results of observations and measurements in science, shows that the world has all possible structures, not just more than one structure, not just multiple structures, but all possible structures. Now, the division of labor between us this afternoon is clear. It's my job in 40 minutes to try to lead you as convincingly as I can from this intuitive premise to this repulsive conclusion. And it's your job, of course, unless you wish to accept this repulsive conclusion, to point out in the discussion session where I've gone wrong, where I've made a mistake in logic, or where I've made an assumption, for example, that appears to lead me to my conclusion, whereas in fact the argument fails. In the language of real patterns, which I'm sure many of you will recognize as a language that's used to a very large extent by researchers at the moment in this field, my repulsive conclusion is that all patterns are real. There are no non-real patterns or no unreal patterns. By real patterns, of course, I, just like the people who use this terminology, mean patterns that contain information about structures in the world, informative patterns. Okay. So those are the aims of the talk. Now I want to give you the argument in a nutshell. This is a quick rendition of the argument, just to show you what the major steps are before I go through it in more detail in the time that remains. So I'm going to start by the assumption that I'm making that any data set, that is to say, I conceptualize a data set as a string of digits, like an extremely long telephone number, for example. And that's the results of observations and measurements collated in a particular way. Any data set can be decomposed, I'll say a little bit more about that later, into any pattern whatsoever, absolutely any pattern, and an accompanying noise term. More about this later. That will be the first step, the first thing that I'm going to try to persuade you of. Then comes a slightly more difficult, for me more challenging stage. I'm going to try to persuade you of the following, that every such distinct pattern into which a data set can be decomposed, together with its accompanying noise term, constitutes equally strong evidence of a structure in the world. So all of these patterns contain evidence about structures in the world. You can't disqualify or cast doubt on any of these patterns as evidential, as having evidential significance about the structure of the world. Moreover, I'm going to try to persuade you that every such distinct pattern constitutes evidence of a distinct structure, constitutes evidence that the world has a distinct structure. There's many patterns, so many structures in the world. And if you put all these things together, and I haven't made any silly blunders, then the conclusion would therefore be that empirical data themselves, not metaphysical speculation, but empirical data, constitute evidence that the world has all structures. This is what I'm going to be taking through the stages of the argument. So let's make a start. And my starting point is empiricism, a fairly standard form of empiricism, which I'm augmenting with an assumption in the second half of this sheet 4, which I'm hoping also most of you will find acceptable. And standard empiricism is, of course, that it's empirical data that contain evidence of structures in the world. We have no access to the world, no epistemic access to the world other than through empirical data. There's no way in which we can kind of open a window, such as the window facing us here, and look outside to see what the world is really like. All our interaction with the world, all the information that we can hope to gain about the world comes in the form of empirical data. So this is a very classic form of empiricism. The addition that I'm making is that evidence of a particular structure in the world takes the form of a pattern, a particular pattern in data. And a pattern in data, I'll say something more about that in a moment or two, but I conceive of a pattern in data as an additive component of the data set, which has a particular simple form. One, for example, that can be expressed in an algebraic or at least an analytic form. And the emphasis on patterns comes because most of us in philosophy of science come to the conclusion that individual data points have little or no evidential significance in scientific practice. Whether a particular data point comes out as a 5 or a 7 isn't very important, isn't very significant, doesn't tell us a lot about the world because of the way in which data are caused by phenomena in the world. It's only the underlying patterns that hope to carry hope to carry evidence about structures in the world. So to give you an example, somebody working in particle physics will point to a certain pattern in a very large body of empirical data and say that that pattern shows, for example, that the Higgs boson exists. And the evidence for the Higgs boson will come in the form of that particular pattern, that additive pattern in the data set. Okay, that's my starting point. Now, the trick then in science, if you strip science down to its fundamental empirical operations, how an empirical form of science is carried out, then the first thing that one does is, of course, find patterns in data. You mine empirical data sets in order to extract patterns from them. And how do you do that? Well, in my conception of patterns, what you do is you decompose an empirical data set. Once again, that's a string of numbers, a bit like a very large telephone number, into 2 or sometimes more additive components. These are components which, if you add them together, recover the original raw empirical data set which you gathered in the course of your observations and measurements. And here I've given you a quick example of that. So you've got the data set on the left-hand side of this, you might describe as a kind of metaphysical equation. And the data set is equal to the sum of these two things. One is the pattern, as I'm going to call it, and the other is the noise term. Just to fill that in to a little extent for you, I've identified in the second line of my example the data set as this function of x. It's a very simple data set. It depends only on the variable x. And f of x is therefore going to be an extremely complex function, probably not expressible analytically. And that captures the entire variation of the data set throughout its extent. And we're going to decompose that into these two components. The first is a very simple harmonic function, a sine and cosine. And then to balance this metaphysical equation, on the right-hand side, I've added r of x, which is what I'm describing as the noise term. Now, I want to be very clear about how the noise term arises. The noise term for me is simply a mathematical remainder. It's what you need to add to the right-hand side of this equation in order to make the equation balance. Clearly, it's not the case in most cases that f of x is equal to the harmonic function. The raw data set is much more complex than a harmonic function for reasons that we'll come to in a moment or two, perhaps. So you need to add on the right-hand side a term that's algorithmically as complex as the data set on the left-hand side, f of x. And R of x takes care of that difference. Some people choose to describe R of x on the right-hand side, this noise term, as an error term. I choose not to do so. I can understand to some extent why people do so, but I think that's misleading. I don't think there's any error here. We're not acting here normatively. We're not seeking to pick out or to identify errors. This is simply the way the mathematics falls out of the situation. So far, so good. But then we come to this mathematical fact. I think what I'm presenting here on this sheet 6 is nothing more than mathematical. And so it seems to me there's not very much debate that can be this can prevail. But we'll see, of course, in the question period what happens. And this is the mathematical fact that we can run the operation that I've just described, this decomposition of the data set into two terms, a pattern term and a noise term, in innumerably many ways. Because any data set, mathematically speaking, can be decomposed into any one of all conceivable patterns. In my example on the previous sheet, I gave you a harmonic function, but that could have been any function whatsoever, of course, as long as I was willing to add the noise term on the right-hand side, R of x, that took care of the balance of the left-hand side and the right-hand side of the equation. So here, just giving you 3 examples, you can decompose one and the same data set into a pattern. The first pattern is going to be called pattern A, together with its associated noise term, noise subscript A, or another pattern, pattern B, might be completely different from pattern A, and its associated noise term, pattern C and its associated noise term, and so on to the list of all conceivable possible patterns. This is just a mathematical fact, descending from the finding, from the observation that this data set, this function f of x on the left-hand side, can of course mathematically be decomposed in many different ways. Scientists are well aware of this, of course, and as we'll see in a couple of examples a little bit later on, scientists are very happy to exploit this multiplicity when it suits them in practice, as we will see. And so I don't think to myself that I'm surprising anybody by pointing out this mathematical finding. But nonetheless, the fact that this decomposition of a data set can be carried out in any one of innumerably many ways, involving any one of all conceivable patterns, does pose a problem to those of us who want to associate a pattern in empirical data set with evidence about the structure in the world. It's to some extent an embarrassing or uncomfortable fact to which we have to respond. How to respond to this multiplicity of patterns? In very general terms, I think there are 2 possible responses to it. The first response, which probably most people entering this field this afternoon thought was the only sensible response, the only response that accorded with the practice of science and the nature of the world, is to say that only some of the patterns in data, or only some of the patterns in terms of which you can decompose an empirical data set, contain evidence about structure in the world, or correspond to structures in the world. Only some of them, not all the infinitely many patterns that you could have used to decompose the data set, but only some of those patterns. And the others are uninformative. The others are don't carry any information about structures in the world. And I think that this is what the real patterns paradigm, there's colleagues of ours who talk in terms of real patterns. This is the point they're making explicit or implicitly. There wouldn't be any point in bringing out a category of real patterns if you didn't think there was also going to be a category of non-real patterns. And therefore, real pattern, that's a kind of an accolade that you attribute to the patterns that are informative about structures in the world. And the other patterns are just idle. They're not informative. That's the first response to this, the finding, this observation of the multiplicity of patterns in terms of which you can decompose a data set. The other response is the following. It's the response of, to some extent, biting the bullet, saying, okay, empiricism has brought us to this point. We're going to trust in empiricism, therefore we're going to accept this implicit conclusion, this implication of empiricism, even though it's at first sight inconvenient or uncomfortable. And that is to say that all patterns, every single one of the patterns in terms of which you can decompose the empirical data set, so not just the harmonic pattern, but any pattern you can think of, carries evidence about structures in the world, corresponds to structures, to a structure in the world. Now, in a sense, I've already given the game away by my spoiler earlier. You already know that my own favorite response is response 2. That's the response I want to try to persuade you of. But I'm going to start by exploring response 1. I'm going to do as fair a job as I can on response 1, and you'll bring me up short if you think I've been unfair or missed things in the discussion period, of course. We're going to start by exploring response 1. That's the response, of course, that only some patterns are informative. Those might be the real patterns, and other patterns are idle or uninformative about structures in the world. I think it's very fair for us to pose a challenge to those of us, those colleagues of ours who tend to response 1, who opt for response 1. If someone is going to tell us that only some patterns in empirical data sets correspond to structures in the world and the others are uninformative, they're bogus patterns in some sense, then I think it's fair to ask them to give us a criterion before we start science, before we start scientific practice, to ask them to give us the criterion that they propose to use to distinguish the real patterns from the non-real patterns, the patterns that correspond to structures in the world from the patterns that don't correspond. So we have to ask them this question: in which respect do patterns that correspond to structures in the world differ from patterns that do not? And I'm going to be quite strict about this challenge, this question. I think that if our colleagues who take this line can't provide a criterion, then we have to conclude that their account is otiose. It doesn't deliver what it's supposed to deliver. It's more rhetoric, if you like, than a serious analysis of the methodology of science. I hope you agree with this. But if not, of course, there'll be an opportunity to hear alternative views a little bit later on. Now, what would count as an answer to this question? What would count as a legitimate answer that would satisfy me and the rest of us, I hope? The answer to the question, how do patterns that correspond to structures in the world differ from other patterns? There are some restrictions on what you can say, it seems to me, as an answer to this question. For example, we can't appeal to knowledge about which structures the world contains. We can't say, for example, well, we know that the Higgs boson exists, supposing we've come to that conclusion, and therefore a pattern that shows that the Higgs boson exists, a pattern in a data set that corresponds to the Higgs boson and its existence, the pattern that provides evidence for the existence of the Higgs boson, that's a real pattern. That's a pattern that contains evidence about the world, whereas other patterns do not. We can't do that because what we're trying to do here is we're trying to build up a metaphysics and simultaneously a methodology of science. And we can't rely on the fruits of science in order to inform this very basic fundamental choice about how we're going to run the methodology of science. If you like, you have to imagine a kind of thought experiment where we haven't started science yet. We're wonderful philosophers and historians of science, but science has not yet got underway, and we are determining, as if this were possible, the ground rules of science before applying these ground rules to the empirical data that's coming in. And if we can't appeal to knowledge about which structures the world contains, because that comes downstream of the work that we're doing now, then we are restricted in answering the question about the distinction between informative and uninformative patterns. We're restricted to information contained in empirical data themselves. Not really surprising for an empiricist. There is no other source of information about the world other than the information contained in empirical data. So we have to look at empirical data. We have to try to mine our empirical data in a clever way to identify this distinction between patterns that do and patterns that don't correspond to structures in the world. Any criterion, therefore, must refer to what I describe as morphological properties of patterns and of noise terms. By morphological properties, I mean, above all, the shape and the size of these things mathematically, or their format and their structure. Those are the only things that nature gives us, in fact, on the basis of which we might legitimately be able to form this criterion, formulate this criterion for distinguishing the patterns of these two sorts. What kinds of properties are these? What properties are these morphological properties that would, in my opinion, be the only legitimate source of a criterion for distinguishing these two classes of patterns? Now, morphological properties of patterns of noise terms include the ones that I've listed here on this sheet 10. The first is, of course, the algorithmic complexity of the pattern that we pick out. So, for example, the harmonic pattern that I gave in my little example to begin with, that has quite low algorithmic complexity. It's a very easy, very simple function. It doesn't take much to encode it or to formulate it. That's a function with low algorithmic complexity. Other functions have much greater algorithmic complexity. You need much more stuff in order to formulate such a pattern, formulate the function that will deliver such a pattern. So we might say that we're going to we're going to discriminate between patterns of different algorithmic complexities in our search for the criterion which patterns do and which patterns don't correspond to structures in the world. Or we could say, no, it's the magnitude of noise that's important. It's the degree of discrepancy between the raw data set in its entirety and the pattern that we propose to pick out of that data set. You might think, for example, that if a pattern is exhibited in a data set with too high a noise level, with a very high noise level, for example, then that means that you are losing contact with reality. You're picking out something that's not an important component, not an important cause of the variation of the data set, and therefore you should be more suspicious of such a pattern. On the other hand, you might also think that if a pattern hugs the data too closely, therefore has a very small discrepancy with the raw data set, you might also be suspicious of that. And a third possibility that I'm listing here is the degree to which the noise term, noise A, shows patterns of its own. There's nothing to stop this noise term in my book showing patterns of its own, to show quite sharp or striking patterns, including correlations with pattern A itself, which sometimes in statistical terms is described as an auto-correlation. So these are the possibilities. Just to remind you, we're still reasoning on behalf of the proponents of response 1, that's the response that only some patterns exhibited by data sets correspond to structures in the world and the others don't. And these are some tools that they can use in order to construct this criterion if they succeed in doing so. Let's look at a couple of these in slightly more detail. First of all, I want to rule out a particular, very simple proposal, and that is that we should have a zero tolerance for noise. The first rudimentary proposal might be to say that a pattern is real if and only if it's exhibited by empirical data with zero noise. That is to say, the R of X term on the right-hand side is equal to 0, and the pattern that you pick out just corresponds to the raw data set. I think we can probably all agree quite quickly that this is very implausible. Science in general is not a project of compressing or recovering raw data sets. Science would look very different if all we did was to try to find a formula to encode or to compress the data that just come in. Just to give you one reason for doubting this, we'll be barred from identifying component causes. Component causes are causes that account for one particular portion of the variation, but not all the variation in a data set. And if you did that, if you do pick out a component cause, then you are in effect suggesting that the rest of the variation accounts for that research project as the noise term. And if the noise term were equal to 0 in all cases, we would never be able to pick out a component cause. And I take it that we do very much want to identify component causes of phenomena around us. So I'm going to rule out this first possibility that somebody might have entertained. More subtle proposals go along the lines that I indicated a moment or two ago. You could claim, for example, that a pattern failed to correspond to a structure. A pattern exhibited in empirical data doesn't correspond to any structure if, for example, it has very high or very low algorithmic complexity. You might be suspicious about patterns that fall into those categories. You might say, as we indicated earlier, that you're going to rule out patterns that are exhibited with very high noise levels, with a very high noise term on the right-hand side, or a pattern that's a noise term that shows patterns of its own. You might be suspicious about that. You might want the noise term to be unanalyzable in some sense, just a residue which doesn't contain any further information about the world. You might argue in those terms. Now, these are subtle proposals and I respect them, but there's one very big fact that stops me from endorsing them. And that is that there's a very great deal of empirical evidence against any proposal of this kind. If you look through the history of science, and especially you look at very good examples of, very strong examples of good science, not borderline science, not fringe science, but massive components of the science that we accept, then you'll find that scientists have discerned patterns in the relevant data sets that have all these properties that you might have been suspicious of. And they have found that such patterns correspond to structures in the world. They've identified, they've assigned structures in the world that these patterns are evidence for. And this means that we can't, it's not plausible to use any of these properties, morphological properties of patterns and their associated noise terms, to eliminate certain patterns as bearing information about structures in the world, because in the past we found these to be a gold mine for just that, for information, for evidence about structures in the world. There are many, many examples in the history of science, but I'm just going to give you two. And both these examples show the way in which scientists return again and again to a data set and analyze it in different ways, pick out different patterns from the same overarching data set, and identify each of these patterns with a significant causal factor, a significant structure in the world. So my first example relates to this very famous chapter in the history of cosmology and particle physics, which is the research on microwave background radiation data. In very many ways, through satellites and observatories of various kinds, we've, over the past decades, compiled a very big data set, kind of all-encompassing data set about the microwave background radiation from the sky, from the universe. And we've analyzed it in many different ways. And if you look at the literature in this area, you'll find that scientists, cosmologists, and astrophysicists have returned again and again to this data set, and they've picked out a different pattern each time, and they've associated each of these patterns with a very significant causal factor in cosmology and astrophysics. So the first thing that you hear, for example, about the microwave background radiation data is that it's flat. It's isotropic, and there's a temperature that's associated to this flatness, and that's 2.7 K, 2.7 Kelvin. That's a pattern that you pick out of the data set. It's a pattern, I think, that's exhibited with a rather high noise level. As you see in a moment, it's not a pattern that hugs the data very closely. It's like a flat line, a horizontal line among the scatter of readings. But nonetheless, scientists have associated this pattern to a significant episode in the history of the universe, and that's matter radiation decoupling. And if you question a scientist, a cosmologist, astrophysicist about this, they'll point out to this, that they'll have the data set in front of them, at least ideally. They will point out the pattern that they're looking at, and that's a horizontal line, the flat line corresponding to 2.7 K. And they'll say, look, that's the evidence for the occurrence of something called matter radiation decoupling in the early history of the universe. We are seeing that pattern is the message, it's the signal from that event. But it doesn't stop there, of course. If you reduce your tolerance for noise to some extent and start hugging the data set a little more closely, then you'll notice that there's a hotspot in one area of the universe, one orientation in the sky, and a cold spot 180 degrees separated from that. And that has a name. That's also a pattern. That's a sinusoidal pattern. It goes up here and it goes down behind us. And it's called a dipole anisotropy. And scientists will pick out that pattern and say that's evidence of something. That's evidence of the Earth's motion relative to matter. Surprisingly mundane thing for astrophysicists and cosmologists to say. But nonetheless, that's that separate component that you pick out. And so it goes on. There's also a quadrupole. That's 2 hot spots and 2 cold spots. These correspond to radio emissions of the Milky Way. There are things which in the technical jargon of this field are called ripples, which are inhomogeneities of the matter distribution, which correspond to a phenomenon, a structure of the universe called inhomogeneities of matter distribution. And finally, I'm not sure if this is the last chapter, but it's one of the later developments. Acoustic oscillations are evidence of the flatness of the universe. All these patterns are to be found in this gigantic data set, this compound data set of all the observations that we've made of this kind. And you pick out each of these patterns. And if you look at each of these patterns, you'll notice that each of them has varying quantities of the various morphological properties that we identified earlier. Some have higher algorithmic complexity, some have lower, because the acoustic oscillations have high algorithmic complexity. The isotropic background that has very low algorithmic complexity. They are manifested with noise terms that are greater or lesser in magnitude. So in general, the more complicated the pattern, the closer that hugs the data, and therefore the smaller is the noise term with which that's associated. And you can look at this graphically. These are just a simple sample of the various graphical renditions of these things. You'll see on the upper left-hand side the flatness, the global isotropy background. That's as simple as it can be, and you get progressively more complicated patterns as you go down the scale, if you like, or up the scale in algorithmic complexity. My second example is it comes from a more mundane area of science, and that's has to do with a big data set of Earth's surface temperatures, where you've collected over decades or centuries data on the surface temperature at Lisbon at noon each day, or frequently than that, if you like. Then you'll find, when you analyze this data set, you'll find many different patterns. It's convenient in this case to talk in terms of the wavelength of the pattern. You've got patterns with a wavelength of a day that corresponds, of course, to the phenomenon that we describe as the Earth's rotation. A wavelength of a few days is of the weather systems that come across Lisbon from the Atlantic. Weather system of the Earth. So Lisbon tends to be warmer in mid-July than it does in mid-November. That corresponds, of course, to the Earth's orbit, and so on it goes. And you get then a picture of this kind. These are all patterns that are picked out from the gigantic data set on these surface temperatures. And you'll notice the variety of patterns. Some of them are algorithmically complex, some of them are less so. Some of them are exhibited with a high noise level, some of them less so. In some cases, the noise term is correlated or shows patterns of its own, including correlations with the pattern picked out. This is so in many cases because, of course, the noise term is nothing other than a buffer to keep the equation so that it the pattern that you pick out. And these are all ways in which I come to the conclusion, therefore, that none of the proposals for a criterion to distinguish informative from uninformative patterns has a chance of succeeding. And it's the history of science and empirical evidence that gives us this basis. I think I should, in view of the time, go through this next sheet extremely quickly, but I'll be very happy to come back to it in the discussion if people are interested. Sometimes when I've given this talk in the past, I've received the objection that I'm looking at science as if it were a one-pass empirical analysis of data, whereas we know that scientific practice is more complex than that. And in particular, you have multiple passes, and there's also a certain amount of diachronicity. You do some things earlier, then you do some things later, and then you compare the outcomes of the two cases. So the first objection that I've received in the past is that scientists pick out patterns partly on theoretical assumptions. I'll come back to this, I promise, in discussion if people are interested. And the second objection is that we discover some patterns to be projectable, that is to say, to support predictions, successful predictions, whereas other patterns don't. And I think there's a good answer to this as well. But I'm going to leave that just for a moment, because I'm interested, therefore, in bringing my discussion to a conclusion and switching to response 2. I don't know whether you agree with me, I'll hear about that a little bit later, but if we think that response 1 is implausible, then we should look at response 2. Response 2 is, of course, the response that says that all patterns in empirical data are equally informative, are real, if you like, constitute evidence about structures in the world. One question is, of course, how many distinct structures is that? We've got very many patterns. What kind of correspondence link is there between patterns on the one hand and structures on the other hand? My proposal is to say that distinct patterns correspond to distinct structures. One reason for thinking that this is a good idea is that as empiricists, we know that we have no access to structures except through patterns. And so it would seem metaphysically a bit suspect to say that we can talk about the identity of structures and collapse those into a smaller number if we're looking at distinct patterns in empirical data which are so guarded. So my advice here is to trust what the empirical data are telling us. And if the empirical data comes up with many different patterns, then we should talk in terms of many different structures. And then we come, of course, if this is the case, we come to the, some people call it kind of startling or worrying, in fact, metaphysical implications of this second response. This is a large pill that you are being asked to swallow. If we agree that all patterns in empirical data constitute evidence about the structure in the world, and we think that each of them constitutes evidence for a different structure, then we come to the conclusion that empirical data contain evidence that the world contains all possible structures. Just for the purposes of the discussion, I propose to call this, to label this view radical polymorphism, because it suggests the world has this polymorphic character. It's radical because there's no end to the range of structures that the world has. And I know, because I've spoken to some of you about this before, that there will probably be two issues in your mind at this point. And these are the two issues that I want to end with. This will bring me to the end of my talk. The first is the relativism question. Is it a form of relativism? Am I acting here, am I talking here as a relativist? And the second question is, you know that magic trick when the magician, the conjurer, borrows your watch, preferably an expensive watch, and he puts it on the table and gives it a great big hit with a hammer, and you see little strings and wheels flying in all directions. The big challenge then is, of course, to reconstitute the watch so that the magician at the end of the show can give you the watch back. And you're in that situation, except that your watch is your familiar experience of the world and society, to some extent, world and science. To some extent, I put that on the table and given it a big hit with my hammer. Now I've got to show you how I can recover that for you and make what I've said, my story, agree with what you know from your everyday experience about science and the world. So that will be the last issue that I discuss. But first, then, the relativism question. Am I a relativist? Is radical polymorphism, as I've decided to name my view, is that relativism? And the answer is no. This is not a form of relativism. Some of you might like it better if it were a form of relativism, but I'm removing even that comfort from you. In radical polymorphism, in the view that I'm sketching here, all structures are absolutely real. They're not real from some perspective. They're absolutely real because empirical evidence, in the very classical sense that we're used to, is giving us evidence. Empirical data are giving us evidence that these structures exist. So you can say a lot about radical polymorphism. You can say, for example, that it's a form of plenism. You can say, for example, that it's too much of everything. You can say that, I can see that. But one thing you can't say about it is that it's relativist. It's not relativism. And moreover, another reason for thinking that this isn't relativism is we can still objectively refute empirical hypotheses, scientific hypotheses. It's true that a data set exhibits every pattern. That's true. But it's not the case that a data set exhibits every pattern with every given noise level. A data set will exhibit some patterns at a lower noise level, other patterns at a higher noise level. And any empirical hypothesis will in fact be a prediction, not just of a pattern, but also of the noise level with which that pattern is exhibited in data. And that's something that can be refuted. And it's these two things, the realness, the reality of all structures that I'm claiming, and also the refutability of empirical hypotheses, that mean that for me this is not a form of relativism. So it's not the case that everything goes in radical polymorphism, far from it. And finally, recovering familiarity. How can I, from the story that I've given you, recover for you your everyday experience of the world and science? Well, this comes in two parts. The first thing to say is that our experience of the world is, in many cases, that it contains complexity on many scales. And we've seen that in the historical examples as I gave you earlier. It's a very familiar experience in science that you go back to a data set that you've analyzed, or your colleagues or predecessors have analyzed in one way, and you pick out a different pattern from that very same data set. And you pick out that pattern with a different noise level from the one that your predecessors had accepted. That just happens every day in science, this reuse of empirical data sets. We're never in a position to say, well, we've dealt with that empirical data set, we've analyzed that exhaustively, we never need to go back to that, because we know that some other research question will lead us, quite likely in the future, to take another look and to pick out certain other structures from that very same data set. And the other thing that I want to say about recovering familiarities is the following. Yes, I've argued that all patterns in the data set are equally real. Every single one of them has claim to the same degree of reality. But of course, they're not equally relevant. They might be unequally relevant to a particular research question or research project. And that means that scientists have the ability, of which they make use in any research project, to pick out certain patterns as being more relevant to their own cognitive and practical interests, and to ask for attention for those particular patterns. And that choice is guided, of course, by pragmatic preferences. For example, preferences for patterns of a certain form, or patterns that are exhibited with a certain noise level. There's nothing wrong with that. That's the way in which science works. It's the only way you can of making sense of reducing the plurality of patterns that nature presents us with. And there's absolutely nothing wrong with that. However, I would say this pragmatic preference is a methodological aspect of science, not a metaphysical aspect of science. That's the way science proceeds, but it gives us no clue, it gives us no guide as to what the world is like, what the metaphysics of empiricism is like, because it's a purely pragmatic preference that you bring to the table, that you bring to the world. It's not something that emerges from the empirical data. Moving now to my conclusion, just 2 more slides to go. If anybody's interested, I have some references. If you want to hear more or look under the bonnet, then there are some references. But now I come to my conclusions. So my conclusions are then the following. You will give me the verdict whether or to what extent I've been able to take you on this journey from, I think, an intuitively appealing set of premises to an odd and maybe even disturbing conclusion. But I've gone through the following stages, it seems to me. I've argued first that all distinct patterns into which empirical data sets can be decomposed have equal evidential status. There's no way of granting some of them evidential status and denying that from other patterns. All patterns are real in that terminology. And moreover, all patterns constitute evidence of distinct structures in the world. I realize I went over that point quite quickly, so very good questions about that. And therefore, my final conclusion is that empirical data, the data we gather in observations and measurements, show that the world has all possible structures. That's what empirical data is shouting to us. Empirical data are not shouting the world has this structure, structure A, or the world has this other structure, structure B. If we listen carefully, we hear the empirical data shouting to us the world has all possible structures. Think about it. And it's our choices among patterns, something that we as cognitive beings bring to the table, that explains our familiar experience of the world and science as privileging sometimes the one structure and sometimes the other structure. That was it. Thank you so much for your attention. Thank you.